Bassam, the floor is yours.
Yeah, thank you, Arnon. I hope you can hear me very well. Thank you for giving me this opportunity to present my team's work here. And yeah, thank you, Christoph, also for rescheduling the timetable to allow me to present in the morning in your time, in the evening here in Germany. I am jealous not to be with you. I wished I could join you in person, but unfortunately I couldn't make it. And that's why I am presenting our work online. So I hope you can see also the slides. Here are some words about my background. I am currently in the computer science department. I am taking care of the cyber physical mobility. And before that, I did mechanical engineering, where I did my PhD about network control systems. And before that, I did computer science with focus on automation engineering, which is more or less control engineering. And you will see my history also in the presentation. So I would like to start the presentation showing this video. I hope you can see it. I hope the internet connection is fine enough. So Patrick, if you cannot see it, just tell me in WhatsApp. We could show it in person there using your laptop. Okay, what we see here is a traffic situation in our cyber physical mobility lab. And my message from this video is to tell you at the end of this hour, you will have the idea how to implement such cool scenarios. And yeah, this is the focus of my group here in Aachen. We combine disciplines, different disciplines in mobility. And the first three are network model predictive control, which is the focus of today's lecture. This one is about software architectures. I mentioned it when speaking about our cyber physical mobility lab. Yeah, let's start. So I would like to introduce the idea of model predictive control very shortly to you. So imagine there is a car driving in this direction and with a constant velocity, and it has to follow this line. And we can measure the difference between the current position and the reference line, and we can use the steering angle to get the vehicle to the reference. What we can do is classical control or predictive control. In classical control, it is similar to drilling a hole in the floor of the vehicle and looking where are we now and correcting the steering angle. And in predictive control, it's more like what we do as humans. We look out of the windshield and we don't drive to the tree. We drive on the lane and we avoid blocked lanes and drive on the free lane. This is a very short introduction to model predictive control. So formally, what we do, we have a reference trajectory. We have in the past measurements, and we use a model to predict the feature of the system. And the model is usually a mathematical model. In many cases, it is a differential equation system. The horizon in which we predict is called the prediction horizon, and we formulate an optimization problem and minimize the difference between the reference trajectory and the measured trajectory or the predicted trajectory using the control input, and we optimize the control input inside what we call control horizon. Mathematically, or what we have seen is an open control problem, open loop control problem. It is not closed loop control, and how we close the loop, we conduct the MPC at every time step. So mathematically, it is this optimization problem. So we have an objective function here. We have constraints, and yeah, we optimize. We use an optimization algorithm to get a series of control inputs. And what we apply in MPC is just the first control input, and in the next sample time, we recompute again. We compute again a series of control inputs and apply always the first one. This is a very short introduction to MPC. And I would like to show you now a situation which you know from everyday life, especially after COVID now, in malls or in city centers when they are crowded. Maybe you have seen it, maybe you have watched it, maybe you have experienced it by yourself. Two pedestrians approach each other, avoid each other once, avoid each other twice, and at the end of the day, they may collide or not. So humans are able to resolve such a situation. But what about pedestrians? How does it work? And if you have been to Japan, and you can go to the Shibuya crossing and observe how does it work in such crowded intersection. And now I would like to move on to a game. I would like you now to think of a number, choose a number between 0 and 100, and the winner of you will be the closest to the half of the average. So every one of you will think of a number. We will take the average of your numbers, take the half of it, and the closest to this number is the winner. So we are not going to do it physically, but just think of a number, take some seconds to think of a number. So fix the number in your head, and we conducted this experiment several times. Here you see 3 experiments, and the winner is always near to 12.5. Why? Because people think the average, if I take random numbers between 0 and 100, is 50, the half of it is 25. So most people will write down 25, but we are asking for the half of the average. And if you have enough coffee in your blood, you will say 12.5. So this is the right answer. And if we repeat this experiment, you would get 6.45, maybe 6.5. It depends on the number of participants. But in general, in the first round, if you don't know this game, or if the participants in general don't know this game, the winner will converge to 12.5 if we have infinite number of participants. And why? What happens there? The decision quality of the individuals are affected by decisions of others. So what you think, what is the right answer, the other people think also about you. What are you thinking? What is the right answer? So you have to think what the other think. And you can continue this recursion. You can say what I think, what the other think, what they think, what I think, and so on. And yeah, where does it come from? The name beauty contest. So it comes from the news later back in the days, they presented some characters and asked people, which is your favorite character? And the winner is the major selected character. So you don't have to, if you want to win, you don't have to choose your favorite character, but the most favorite character of the people participating in the game. You can also compare stock market, it works very similar. So now we can get to a definition, not formal, but a definition of network systems. And during this lecture, if I say network systems or connected systems or connected vehicles or networked vehicles, they are always the same. Network systems comes from the control area where we speak about network control systems, and connected is more the used term in vehicles. So we speak more about connected vehicles than about networked vehicles. So they always consist of communication. They have interacting systems. And why do we study them? They should contribute to better perception and decision making. And in my lecture today, I'm focusing on the decision making. And many challenges come with the network of the system, and they are arising from computation time and communication. So we will have to deal with feasibility and quality issues. I'll show them to you in some seconds. But first, an example of from connected and automated vehicles. Here is the typical example in perception. So vehicle number 1 is driving to the north, 3 to the south, and 2 is stopping here. The pedestrian is trying to cross the street, and vehicle 1 cannot, the sensors of vehicle 1 cannot see the pedestrian because it's covered from vehicle number 2. So vehicle number 3 can tell 1, okay, there is a pedestrian, slow down. And from the area of decision making, the typical example is the intersection. So vehicles are crossing an intersection that they have to cross it safely and efficiently. And of course, safely means in first line, don't collide with each other. So in my group, we study or we decompose this problem into 3 levels. We have the methods, the applications, and the experiments. On the level of the methods, we try to reduce the computation time and communication to be able to apply the methods in reality. And at the same time, we try to enhance the feasibility and quality. So always there is a trade-off, or in most times there is a trade-off between computation, communication, and quality. So we apply our methods to different applications where we use optimization methods, and also we apply our applications, or we study our applications in experiments in our cyber physical mobility lab. So here is a classification of network control systems, how we study them in our group. So we study network control systems which consist of homogeneous dynamics. They are dynamically decoupled like vehicles, and the coupling is in MPC in the objective function or in the constraints. So we focus on network model predictive control, and there we focus on distributed, more specifically network control. And okay, I should turn off my video. So I hope you can hear me now better. Give me a sign, Patrick, if I should continue.
Yeah.
Okay. So, and we study cooperative and non-cooperative strategies. Yeah, a note. Cooperative and non-cooperative, the terms here come from game theory, and in terms of trajectory planning, non-cooperative strategies result in also cooperative trajectories, but here the terms come from asset game theory. So, and we look also on the algorithm level, on different algorithms, how we can get to good solutions. How can we embed our network system in the MPC? Every term here in the equations you see is the MPC, and the network terms are in the objective here or in the constraints. So what is the advantage of this formulation? We can deal with the action of other agents with respect to their feature intention while making decisions of the agent's own control actions. We will see some examples about this. Yeah, now we have formulated the MPC and put the network terms into it. How can we formulate now the optimization problem? We can formulate it as a centralized MPC, where we have a center where we collect the information of all agents, solve the optimization problem, communicate the results to the agents, and they apply. So this is not applicable in practice. It has a high computation time, and we have single point of failure in the center. Nevertheless, we solve such an optimization problem to use it as a benchmark for comparing different distributed MPC strategies. Yeah, further strategy is the cooperative distributed MPC. So we decompose the centralized MPC into smaller optimization problems. So each agent considers itself and its neighbors, but always keep this in mind. Every agent applies only its own control input and throw away the plans of other agents. They are just made to predict the feature intentions of other agents. Now I would like to introduce a term to you. It's called prediction consistency. So it means that the predictions used or computed in the optimization problem of an agent VI at a time instance T for an agent VJ coincide with the predictions computed by agent VJ itself at the same time instant. So it means, with other words, what I think about you, you think about yourself. So my plan about you is your plan about yourself. And this property is very important. Without the satisfaction of this property, no guarantee for NCS stability and feasibility is possible. Cooperative MPC, as I presented it, doesn't satisfy this prediction consistency property in general. There is an exception. If the NCS is fully connected, the cooperative DMPC becomes CMPC, except the communication structure, of course, and it has a high computation time. So we don't want to have that. Yeah, why it is not prediction consistent? Here is an example made by my group member, Max Klook. He is sitting around there. Yeah, here we see the perspective of agent VA. It sees itself, of course, VC, VB, and VD, and its neighbor, VB, sees VC, VA, VE, VF. So there are two agents seen by VB, not seen by VA, and this leads to the loss of the prediction consistency. What can we do to get rid of this inconsistency? We can solve in sequence and iterate. This is the general proposed solution in the literature, but it has a high computation time. Max Klook came with an idea to use synchronization in cooperative DMPC to get feasible solutions. And what he thought to synchronize is not the plans of the agents, but I synchronize my plan about, or the plan of agent A is synchronized with the plan of agent, again, the plan of agent A about B is synchronized with the plan of agent B. So they synchronize what they think about each other, and they don't synchronize their plans as in classical synchronization. This is very smart solution. Of course, we have to iterate there. He makes local plans in parallel and synchronize the decisions with the neighbors. Max studied also the graph structure, studied graph properties, which conditions should be fulfilled to get a feasible solution, and to reduce also the computation time, and came up with an idea of also creating a coupling topology if one doesn't exist, using non-cooperative games. So you can read more about it in this paper presented at the IV this year. Cooperative DMPC is could produce good solutions, but there is also another option which reduce the computation time further, is the non-cooperative DMPC. We decompose the centralized MPC into smaller optimization problems. Each agent considers own objective, own constraints, and the coupling objectives and constraints with neighbors, and they communicate their optimized predictions. So an agent tells other agents, this is my plan, and they use this plan to consider this agent. And this is a greedy algorithm because each agent considers its own objective and only a prediction made by other agents. This comes with time delay, and the time delay leads to prediction inconsistency. And the non-cooperative DMPC doesn't satisfy the prediction consistency property due to the time delay in the communication. And I would like to visualize this using this example. So here we see an example of two vehicles, V1 and V2. They move exactly with the same velocity. The vehicles are located symmetrically with respect to the vertical axis. And we assume a time delay of 1 time step. So the vehicles should move straight. So this is the reference trajectories of the vehicles. So in the first time step, there is no conflict. The vehicles plan to move straight. In the second time step, they detect, okay, there is a collision and we should avoid it. And they decide to avoid it to the south. And this leads to a conflict. Because they knew the plan from the other agent that the other agent is going to stay on the straight line. So because this is a greedy algorithm, each agent thinks in the next step, okay, the other agent is going to avoid the collision. I can turn back to my reference, and this happens again and again and again till the collision cannot be avoided anymore. What can we do? We studied the graph structure, and we observed that the graph structure of such problems is cyclic. So it contains cycles, and which means that we consider exactly the same coupling in both agents. And we showed that cycles in coupling graphs lead to loss of prediction consistency property. And what can we do to resolve this problem? We can solve in sequence and iterate till we get to a solution. It comes with high computation time. And our proposed solution is the priority-based non-cooperative distributed MPC. I would speak about priority MPC, so to simplify this term. If the network is time invariant, we're done, and we can solve the optimization problems in parallel. But if the network is time variant, we need to solve in sequence, and then we get again high computation time. What can we do to reduce the computation time in sequential computations? We observed that the priorities generate partial order. We can convert the partial order into a topological order, and this is only possible if we can prove that our graph is a directed acyclic graph. So we could prove this, that the graph generated using coupling, using priorities, is a directed acyclic graph. And what can we do with this information? The good news, our topological order is not unique because the graph is not fully connected. So we can use this to reduce the computation time. I give you here an example. Look at agents 2 and 3. There is no edge between them, and they are independent. So they could compute in sequence after V1 because both depend on V1. And V4 computes after V2 and V3 because V4 depends on them. So we found an algorithm how we can generalize this. How can we generate a topological order from a graph? And in this case, V1 can compute first, then V2 and V3, then V4. Yeah, and a remark, if we can assume that V1 has a good controller, then V1 and V2 and V3 could compute also in parallel, because we could trust the prediction of V1 if its controller is good. So then came Patrick Scheffel, who is sitting around you, and came with the idea, okay, how can we distribute the priorities to get always a solution? So we could show that using priorities, we could reduce the computation time, but how about the feasibility? And he came with the idea to use the predictions to assist if there is conflict between the agents, and depending on the conflicts, he distribute priorities. And if we don't get a solution, because we cannot guarantee here always to get solutions, we can propose always better and better algorithms, and we can use heuristics, propose new heuristics, good heuristics maybe, but we cannot guarantee finding a solution because the problem is in p-hard, and if we could propose a solution, we could win the well-known $1 million prize, $1 million, of course. And Patrick presented his solution or is going to present it in the ITSC this year. And the main focus of his work is how can we guarantee or study the recursive feasibility of the network control system. Recursive feasibility means if we get a solution at a time instant t, what can we say about the solution of the time step t+1? Can we guarantee to get a solution at t+1? How good is the solution there? And this is defined as the recursive feasibility. The recursive feasibility is well known in the area of MPC. There is the question in a single MPC, I get a solution at a time instant t. Can I guarantee to get a solution at a time instant t plus 1? And he extended this definition to network control systems. And looking at the priorities, we asked ourselves if we could reduce the computation time, if we can get the computation time more reduced. And here you see an example graph with 4 nodes. And with the priorities distributed here, if we assume that the vertex number is the priority of the vertex, then we get a result 4 levels of computations. So V2 needs to wait for V1, V3 needs to wait for V2, and V4 needs to wait for all of the agents. Yeah, we found out that we can distribute the priorities in other way to reduce the levels, but also we can redistribute the priorities also to reduce the incoming edges. The incoming edges are in the constraints in the optimization problem, and it's well known that the number of constraints in an optimization problem increases the computation time. So Patrick studied this and came up with the idea of graph coloring, and he proved in his publication, which is still in preprint, that it is equivalent to graph coloring. Graph coloring is a well-known problem, and we can use heuristics from the field of graph theory in our problem. Well, and now we are almost in the middle of my presentation. I would like to give you an active break. Here is a problem, a chess problem. So here, assume you are the white player. So you're playing with the white figures. And I need you to think of a solution where we can get checkmate in 2 moves. So discuss this with your seatmate and find a solution. You will have some seconds. I have a break. You have an active break thinking about a solution. So I hope the problem is clear. Yeah, we are playing chess. We arrived at this stage of the game. You're playing with the white figures, and I am asking you to find a solution where you can arrive at checkmate in 2 moves. And please discuss it with your seatmate. So do you have a solution? If you have a solution, you can present it. So I can't see you. I hope you are reacting to this.
No, because when you come to bishops, We brought the keyboards.
So I heard somebody saying bishop to d3.
Then the horse to c5.
Say it again.
The horse in a4 to c5.
C5.
No.
Queen to b3.
Yeah, it could be a solution. I don't know exactly. I have to examine it. This is not the solution I have found. I will show you in a minute the solution I have found. But why I asked you to play this game? What you actually did is a networked MPC. So you have a model of the chess game. You use this model to formulate your optimization problem. You have an objective. You have also constraints where to move the figures, for example. You have limited time to solve the optimization problem, and you have also to interact with the other player. And that's why I asked you also to discuss this with your seatmate. Yeah, the solution I have is this one: move the bishop to d3 and the queen to c2. Feel free to take a photo of this slide, and if you would like to discuss it later or to think more deeply about it later during the next break. So I'll move on now to the next slide. I hope you had enough time to take a photo. If not, just ask Patrick. He can provide you with the slide. By the way, we can provide you with all the slides, of course. So we have many examples where we showed that our strategies work. Here are some YouTube links. I'm not going to show you the videos. Yeah, just search there for example, my name, and you can find a lot of videos. I have also created a playlist where you can see some of our results. Our methods, especially our distributed MPC, could also be applied to other fields. One former student of mine could apply it to airborne wind energy also. It's not only applicable to connected and autonomous vehicles. And here we see some examples where we could apply our distributed MPC. On the left, you see an intersection, and the task of the vehicles is to cross the intersection safely and efficiently. Yeah, and on the right-hand side, you see an example of go-to formation. Go-to formation is defined as follows: distribute vehicles randomly, define target positions or also orientations. We call them both, the combination of position and orientation. And the task of the vehicles is to drive also safely and efficiently to their goal positions. We applied it also to the racing of multiple vehicles. This is very exciting because the vehicles have to drive as fast as possible around the racing track, but at the same time, they have to coordinate to not collide with each other. So at the same time, they have to compete and to coordinate. This is very exciting. We have published a paper in the Transactions on IV this year on this topic. So now it's time for questions. So I have more slides, but I will give you now the opportunity. If you would have questions till this part, I would be very happy to answer them, because I am after this slide, I'll move on to another topic.
I have one question on
Yes,
the
please.
priority assignment. I mean, you did that graph base by minimizing the number of incoming edges or something like that. But could you also take the traffic oriented optimization, saying, okay, I want to minimize traveling time or I want to maximize distance between vehicles or anything like that?
Yes, it's a very good question. We asked ourselves this question when we applied it to the crossing example exactly here. And yeah, we had some rules how to distribute the priorities, and yeah, they were dependent on the traveling time, on the velocity also. We assumed that faster vehicles to break them down costs energy, so we need to give them, for example, yeah, higher priorities. Does it answer your question?
Yeah, thanks.
Yeah, welcome. Okay, you can still ask questions about this part after the whole presentation. And now I'll tell you, yeah, the simulations are very nice, but not exciting enough. That was our motivation to construct our cyber-physical mobility lab. We can, of course, study or experiment in real world, but it is very expensive, very difficult. You need a fleet of connected and autonomous vehicles, you need a test track, and so on. Simulations are somehow, to be honest, boring. So we came with the idea to have an accessible platform, which we call our cyber physical mobility lab. It is here in our building, in a room of size 6 by 7 meters, and we drive on an area of 4 by 5 meters approximately. Yeah, and here I would like to present some of the features of our cyber physical mobility lab. So first point, it is open source. So from day one, we opened everything, code, plans, documentation, everything is open. We wanted that everyone in the world could rebuild our lab. But after some time, we realized that it is really costly. It costs a lot of time, more than planned. It costs a lot of money to build such a lab, and that's why we started working on a remote access to the lab, and now it is available. So our lab can also be accessed via the web. But about the lab, it consists of 20 model scale vehicles, which we call µCars. We support centralized and distributed computations in many ways, hybrid computations of parallel or sequential computations. And what we use in our lab is a modern architecture. We call it our hierarchical service-oriented architecture. It consists of high level for complex computations, mid and low level. Yeah, we use a middleware for data exchange and synchronization, which is based on DDS. I will present it in a second, but the functional architecture of our lab is based on Science Plan Act. We also define an infrastructure part, and it is, I want to tell you that it is modular, so you can replace any module in the software of the lab and implement your own code. Of course, our focus in the lab is on the coordination and decision making. And we use as an architecture or for the data exchange, the well-known data distribution service. It is also used in ROS2, and we used also in our big project µCars Agile, where we developed a service-oriented architecture for autonomous vehicles. I think more about this topic will be taught today by Jan Becker. So back to the hardware in the lab. This is our vehicle in the lab, our µCars. It is based on an off-the-shelf racing model scale vehicle. Yeah, we redesigned it to be connected and autonomous. So here you see where we placed the battery, our servo for the steering, our driving motor. We designed also our own PCP, where we placed our Raspberry Pi 0W. W stands for wireless, so this is for the communication of the vehicles. We equipped the vehicle also, or each vehicle, with an IMU. We have a motor driver, and for low-level hardware abstraction, we use an Atmega. We designed also, here 3D printed for to place the LEDs on it, and we use 4 LEDs to detect the position, orientation, and ID of the vehicle. So the outer LEDs, they are used to compute the positions and orientations of the vehicles, and the middle LED flashes in different frequencies to detect the ID of the vehicle. And here we see our Hall effect sensors to compute the rotation speed of the motor. We have designed also an indoor position system. We have a camera in the ceiling of the room, and it detects the LEDs. So it was some work to get it working. You can try to detect here the number of vehicles and their IDs, and which LED belongs to which vehicle. So it is an exciting problem. And now again, the video I showed at the beginning of this presentation. So this video is based on the work of Patrick. The vehicles avoid collisions based on our priority based Net-MPC. We have here in our lab this scenario, or this map. We can replace the map. Here we have on the outer, we have our highway, and here in the middle is our intersection. We have also highway entrances and exits. And the task of the vehicles is to drive safely and efficiently. In this testing scenario, the vehicles are allowed to change the lanes randomly, and also the next path in the map is also chosen randomly. This is our testing algorithm, and as you see, it works with here 15 µCars. They drive fast and avoid each other. How does it feel to be inside of one of the µCars? Here you can have an impression of it. So it is very fast. You maybe feel bad looking for long at this video because for a situation like this one. And we are using also the lab in a project with Frank Flemish, who presented his work yesterday, to study also human factors. how can we use the lab? We can also use the lab for PR, for public relations. We use it in the anniversary of the 150 years of RWTH, and here you see Ms. Reeves, Shari Reeves. It's a well-known journalist in Germany, and we model scaled her also on our racetrack. What else? How can we use our lab? We can use it also in project meetings to organize workshops, or also to take project pictures. So here you see Christoph and Oliver, and also Catherine in our lab waving at the camera. So what do we need to build such a lab? We need sense, plan, act, and also for connected autonomous vehicles, you need a good software architecture to have a platform where you can implement your algorithms. And also we need to consider the humans. So in our lab, we are considering these 3 building blocks: sense, plan, act, architecture, and human factors. Now, here you see a world map to map our outreach of the lab. You see the number of visits, downloads, and the countries where we outreached our lab. On our website, you can also find a full course, also an EECI IGSC. Maybe this is a password for some of you. It is the European Embedded Control Institute. It offers courses. They are called International Graduate Schools on Control. They are 1-week courses. One of them you can find online. We offered 2 years ago. And next year, we are going to offer it again in person. So you are welcome to track the website of the EECI and to register to our course and see the lab in person. What we are planning for next year also is a CPM Olympics using our remote access. And we are planning to host a workshop in the next IV in Alaska, and where the best 3 solutions or up to 5 solutions can present their work. And there are some prizes we are organizing right now. So stay tuned to our lab at this link, CPM, and so on. Yeah, and now I would like to summarize my presentation. I presented methods for distributed MPC. They are cooperative, and we use synchronization to improve the cooperation and to reduce the computation time and enhance the feasibility and quality. And also non-cooperative DMPC, I've presented the priority-based one, which is the work of Patrick Scheffer. He's around you. You can talk to him today. The work on cooperative DMPC is the work of Maximilian Klug. He's also around you. Feel free to talk to both of them. We applied our methods also in applications of connected and autonomous vehicles, and also brought them into experiments in our lab. So what next? What are the challenges? If you are a PhD student in an early stage of your PhD, you may are looking for open topics in this area. I'll mention some of them. So one is to reduce the computation time. Here you can also look at the work of Oliver Brinkman, who is also going to present tomorrow about accelerating the machine learning using special hardware. And here it is a possibility for cooperation. also the communication is very crucial in such an application, and we also are cooperating in our project, in our SPP with Andreas Festag. You learned about communication, I think yesterday was his presentation. And also the next challenges are safety and efficiency. I think you have learned about safety yesterday in the presentation of YBIN. And of course, open topics are tools and applications. With tools, I mean software tools, especially for building the architecture, for inappropriate architecture, for good software to map sense plan act very well. Yeah, here you can also look today at the presentation of Jan Becker, and also bringing our methods into application is also a challenge in the next year. And here we are also cooperating with people like Christoph Stiller, and we look also at the work of Arnold. So it is a very exciting topic with many open challenges for the next years, and also for cooperation. So that's all from my side. I would like to thank my group members. This is a teamwork what I presented, and also some advertisement. We are hiring now, so if I got you excited, feel free to talk to me or in person to Patrick and Max. They will tell you about our projects. With this, I thank you very much for listening. I thank you for giving me the opportunity to present my team's work. And I am very happy to discuss with you now.